Hello, and welcome to the Sentinel Innovation and Methods Seminar Series. I'm David Carroll from Kaiser Permanente, Washington, and I'll be moderating today's session. As many of you know, the U.S. Food and Drug Administration Sentinel system helps to address questions related to the safety and effectiveness of marketed medical products. The Sentinel Innovation Center focuses on developing innovative methods to further advance Sentinel. And this is done by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities through these advanced analytic methods. Another component of the Sentinel system, the Sentinel Operations Center, focuses on supporting FDA in the use of the Sentinel Common Data Model and the associated modular programs or tools to gather evidence to support regulatory decision-making. The Sentinel Operations Center maintains FDA's Active Risk Identification and Analysis, or RAS system as well. We launched this webinar series to engage experts and innovators in key areas related to the Innovation Center's master plan and the Operations Center's methods work. With that, I'm pleased to introduce to you today our speaker, Dr. Hong Yu. Dr. Yu is an elected fellow of the American College of Medical Informatics and is director of the Center for Biomedical and Health Research in Data Sciences and professor of computer science at the University of Massachusetts at Lowell. Dr. Yu is also a research health scientist in the Center for Healthcare Organization and Implementation Research at the Veterans Administration Bedford Healthcare System. Dr. Yu holds adjunct professor positions at the University of Massachusetts Medical Center and Amherst, and is a PI or multiple PI on several NIH-funded research projects, and has authored over 200 peer-reviewed publications in leading computer science and biomedical informatics journals and conference proceedings. The title of today's presentation is Natural Language Processing for EHR-based Pharmacovigilance, Current Progress and Future Directions. And like me, I'm sure you all are eager to hear what Dr. Yu has to share with us on this important topic. Before we get started, I'd like to mention to you that all lines are muted. If you'd like to pose a question, please type it into the Zoom Q&A feature in your interface, and we will answer questions at the end of the session. And finally, one note, this session is being recorded and will be made available through the Sentinel webpage after the meeting, which can be found at sentinelinitiative, all one word, .org. So without further ado, Dr. Yu, thank you so much for joining us today, and I'll turn this over to you.
Thank you so much. It's such an honor to present in this, to this wonderful group. And so here I get started. So the only thing is not, slide is not working. Can I quickly?
Megan, would you mind advancing the slides, please?
Sure, 1 second.
Yeah, do you want me to try it one more time? Just my side. Okay, let me see. Okay, so today I'm going to talk about natural language processing for EHR-based pharmacovigilance, current progress and future directions. And so this is a collaboration with my students and other faculty members. And so my group is called UMass Bio NLP. And so before I talk about our work, and so here I have no conflict of interest and to report. And the views, opinions expressed in these presentations are my personal views and opinions that must not be construed as representing the views and opinions of any institute from which I have received funding or with which I am or have been affiliated in my professional life. So pharmacovigilance is the science and activities related to the detection, assessment, and understanding and prevention of adverse effects or any other drug-related problems. Traditional sources of information and for pharmacovigilance include clinical trial, pharmaceutical industry reports and adverse event spontaneous reporting databases. And electronic health records has been formidable and resources and for pharmacovigilance. And so, and for the notes, and study have found that electronic health records notes contain rich descriptions and relate to adverse events and frequently not available in the structured data. So the main focus of my research group and relate to the pharmacovigilance is to develop natural language processing system and to help in unlocking this valuable information in the notes to help in pharmacovigilance. Somehow I cannot move the slides again. So and
I can share my screen. That's
yeah, let me stop sharing.
Are you able to see the screen?
Yes, I can see your name.
Shamika, are you able to see the screen? It says that I'm sharing.
I'm not able to see the screen.
No, we haven't. We can only see your name.
Okay, yeah,
Okay.
now I can. Yeah, now I can see.
Oh, can you put the PPT file? Yes. Okay. Thank you. Okay. Yeah. Okay. Going to the next slide. So pharmacovigilance has been active research, and so here is the PubMed records and how many publications and using the keyword pharmacovigilance. You can see that's almost linear growth and starting from 2009 and until now. And so most recently, and the work related to pharmacovigilance is what I found is mostly COVID-19 related. And next one. Next slide. So in contrast, and so what you show here is the number of publications that using NLP and keywords NLP and pharmacovigilance. So it's at 100 times scale less. And so which means is that, so we see there's almost like 1,400 and publications in 2020. And so, and then the number of publications of NLP and pharmacovigilance only 4. And the highest number of publication of NLP pharmacovigilance is 2019. That's only 11 publications. So what happened? So today we're going to talk about my group's efforts and in this area, and so how we can achieve and developing natural language processing for pharmacovigilance. So the outline of talk today, including that, and first I'm going to talk about a cohort we have built called MATE 1.0 for medication and adverse drug events, and then and talk about the result of NLP challenges we hosted and to use this cohort as a benchmark data set. And then I talk about that, and we use NLP to extract adverse drug events from electronic healthcare records and what are the performance and what ADE we have extracted. And finally, and for the methodology of NLP and machine learning, I'm talking about Naranjo question answering. And then I switched to calculate, talk about calibration methods for natural language processing. And okay, so and then the membership inference attack susceptibility for NLP. Next one, please. So first, I'm going to talk about detecting medication and adverse drug event from electronic health records, and so called MAID 1.0 challenge. Next one. So when we work on medication adverse drug event, we decide to develop supervised machine learning. For supervised machine learning, you need to have data for training. So therefore that, and we create a cohort which comprises over 1,000 EHR notes and from 21 patients and with cancer. And so that would so we annotated this cohort, and this result and about 80,000 and named entities, and which I'll describe in more detail later, and annotated with 9 named entity relationship and 9 named entity types, and more than 27,000 relationship between named entities with 7 relation types. And so we host a shared task focused on extracting fine-grained entity information related to medication and adverse drug events. Next one. So some sample sentence and annotation from our cohort. And so, for example, we annotate and at sentence level, and mostly, and all those is in the context of EHR notes. So for example, here the sentence is hypertension is well controlled on current dose of antanolol and 15 milligram daily, and doxazosin and 4 milligram daily. So that's the input of the sentence. So the output is structured output, and which means is that named entities include indications is hypertension and drug name and dosage frequency, and a relationship, and including and the reasons, and which the indications and the relationship and dosage relationship and frequency relationship for these examples. Next one. So in all, we annotate and total 4 events, and one is adverse drug events, and second one is indications, and third one is other signs and symptoms, and the fourth one is medication event. And then for those events, and we have attributes, and for each event. So for example, like severity is attribute for adverse drug event, indications, and other signs and symptoms. Well, duration and dose, route, and frequency are the attributes for medication. So from those entities, and so we have 7 relationship types, and they are medication and dosage, and medication route, and medication frequency, medication duration, and other signs, and clinical signs and symptoms, and with severity, and medication with adverse event, and medication with indication. Next one. So those are the annotation statistics. The statistics of our cohort, recorded cohort is from over 1,000 EHR notes. So these EHR notes, we have totally annotated over 79,000 named entities. So those named entities record that 9 entity types like ADE, indications, and other signs, symptoms, severity, drug name, dosage, duration, frequency, and route. And also relation type, and so including ADE, drug name, and other signs, disease, and severity, and drug name, route, and etc. And so well, we found the most and highest number of annotation for relationship type is drug name and dosage, and the lowest one is drug name and durations. And so, and ADE with the drug name actually represent a total of more than 2,000 annotations. And so all those annotations actually coming from over 1,000 notes. And so which shows that, and those ADEs and are richly described in EHR notes. Next one. So with this, and we call for international and challenging tasks, and with 3 tasks. So the first one is name and entity recognitions, the second one relation identifications, and third one is relation identification, and is joint learning. So you have to identify both name entity and relation in jointly, and so here is 2 separate tasks. So here, the task 1 only identify name entities, task 2 only identify relationship, and task 3 identify both. So the evaluation metrics, and so micro average, and so using exact phrase space and evaluation for standard check, and the test data. So for those training data, we also get, and for those cohort, we split into training and testing data. And so the testing data, and we extracted from using like 3 patients, like the completed data EHR notes from 3 patients, and plus 4 notes from each of the remaining 18 patients. So remember, like those, and we have 21 patients. We take longitudinal data from those patients because and for the purpose, because lots of time pharmacovigilance and can be based on longitudinal information. So the training data is total over 800 notes. And then we release the training data to the community. And so there are over, I think, 17 team, and they registered. And so eventually we have 10 team complete the name entity recognition task, and 5 team completed and relation identification task, and 4 team complete both name entity plus relation identification. Next one. So here are the result. And so this is the best result for that competition, which was held in between, I think sometimes in 2018. And so it is for the first one, the entity recognition task we got. So this is F score. Remember we talk about micro average F score using exact phrase matching. So this is exact phrase matching. So what does it mean? So it means it has to match every single token. So if you have ADE, for example, 5 tokens long, and you have to identify exact token and for those 5 and to be qualified to be correct answer. So that's not an easy task, but we got very good performance, so which is close to 0.83 F score, and the team is from Worcester Polytech Institute. And for the second one, relation identification only, so it's a team of Utah and got 0.86, 0.87, like the F score. And for when you combine both and the task, and so the best team is from IBM Research, and that got 0.60, 17 and F score. Next one. So those are the approaches, like methods, like all the teams have been using. So here is different models, and so with like LSTM and CRF, and also some with linguistic features and others, and so the features including like some feature engineering, and then some of the people, they don't have, they just using deep learning and create end-to-end system. And then for the relation identify, so actually the system, so not deep learning based, but using random forest and for that computation. And it's combined, of using some sort of deep learning and versus traditional machine learning approaches. But note that, so this was a few years old, and so now the best machine and NLP system can perform much better, and with sophisticated pre-trained language models such as large, like BERT and Robota and other, so this kind of like a transformer or bidirectional transformer-based approach, which I will bring up later on in the talk. Next one. So throughout the competitions, and team received the data for training, so they discover a few inconsistencies. So the team considered the cohort, annotated cohort, of high quality, and so they're very happy with the cohort that they received. And so they did find a few inconsistencies. And so, for example, inconsistencies is a few inconsistencies with in terms of inclusion of period. And so for example, P and that all that, and whether that this period has not been included, and for it should be included. And so there are some others, like whether you should and so should include so this term only or include both, because this means the same thing of this. And So there are one or two cases there, inconsistency that, some cases we include this, and not cases we include all of them. And also there are some confusion about double annotations, and so whether particular entities should have two labels or versus one, because when you have two labels, and because when you do name entity recognition task as a single task, and then so because you could only assign one label to this, and that would introduce a little bit confusion. Next one. So with the completion of the of the NLP testing, we see like a team has achieved a reasonably good performance. And so my own team, so we have published our work 2016 and with deep learning models and the relation identification. So we went ahead to process over 200,000 patients and from the UMass Memorial Hospitals, and so that's during the years I think it's between 2013 2015. So and we have about and close to 2.5 million notes and for those patients, and so those patients, they are just all the patients, and including every disease that we all the patients that we have from the hospital. And so from those 2.5 million notes, so we are able to extract over 2.5 million medication and adverse drug event pairs. And so analyzing those ADE pairs, we found the most frequent ADE actually is allergy. It's like particular medication and allergy. And so after we exclude this one, because there are lots of different medication and allergy and medication allergy, so that's a lot of them. So the remaining most frequent ADEs and show on the right-hand side here. So we I know there are lots of in the audience must be a lot of experts in terms of medication and adverse drug events. So this one will be public available, and so we will be released everything we extracted out and in a paper, and so hopefully that people can look into this. But what we look at, next one. So what we look at, there are some positive examples. There are lots of positive examples, and so we found that there are some literature support and so on. And so there are some negative examples mostly, and so negative examples are two type of we consider like could be challenging. One is that whether particular ADE is actually ADE or indication. So sometimes like it's hard for NLP to separate the two. And so, and it would introduce like some false positive, like, there are indications, but actually misjudged to be ADE. And then a lot of times this ADE, they're very generic. So they are not specific. For example, would be systematic disease. So it's not specific ADE. And so, the drug is aspirin and it cause systematic disease. And so they are generic ADE, they are not specific ADE. So that's some of the things we found in the notes. So with this, and so we have this, large and extracted ADEs. And so we use kind of like distributional sampling and to get 120 and extracted unique ADEs based on the distributions. And so, and we give two different physicians. And so they have to judge independently whether each extracted ADE, they are true ADE or not. So one physician judged 115, and out of 120 to be yes, and only 5 to be no. So which represent actually highly, very good, and accuracy. And so we actually we are thrilled and surprised and thrilled at the same time. So the second physician and judge like 18. So note that we didn't do any filtering. So for those, and so that's why we are thrilled and surprised at the same time. So the second physician and judge 18 to be no, and 49 to be yes, and 53 to be unevaluable, because the second physician used the criteria called Naranjo, so which I'll describe for the next slide. Next. So we went ahead and Yeah, we went through called Naranjo question answering. So what is Naranjo? So Naranjo was is a physician, and so he published 1981 a method for estimating probability of adverse drug reactions. So the challenge of adverse drug events is that, and so my understanding is that, and so if you give in to different physicians, and lots of time you have different conclusions, and so therefore this scale and divided by this physician Naranjo is that so a physician can be trained using this scale and to judge the causality and the the likelihood that a particular adverse event is caused by particular medications, and then so physician and the agreement between physicians and are likely to be high, and so therefore that it has been established and as a proper scale and to be used for pharmacovigilance. And so Naranjo has 10 questions which are shown here. So basically you just ask each question. So each question would have based on the answer would have assigned specific score. For example, for question 1, it would be, are there previous conclusive reports on this reaction? So if the answer is yes, you get a positive score of 1, and if your answer is no, you get a 0. And if you do not know the answer, it is 0. And then so others, so for example, for question 2, did adverse event occur after suspended drug was administered? So if the answer is no, you get negative score. So at the end of, after you finish those 10 questions, you just add up the score. Next. And then you would fall into 4 categories, such as doubtful, which, if you have a score 0 or below, and possible if the score is falling between 1 and 4, and probable is score is between 5 to 8, and definitely is score above 9 and equal above 9. So this kind of scale has been used, and so it's specifically those kind of scale has been consistent among different physicians when we evaluate patients, and so that's why it has been established Naranjo as one of a good way and to establish causality between medication and adverse event. Next. However, so for our EHR notes and, based on electronic health records, so we found although this Naranjo, and 10 questions, we found that lots of questions, they might not be the best and for using EHR and, in EHR notes. And so for example, like, are there previous conclusive reports on this reaction? So this one would, you will not be able to answer from clinical notes. And so some questions such as, did the reaction reappear when the placebo was given? So it is, most likely will not appear in the EHR notes either. And then several other questions, and they just have few cases, so did adverse drug reaction reappear when the drug was re-administered? So since we only have like, a few years longitudinal data, maybe if you have many years longitudinal data, maybe you're lucky you found 1 or 2, but most likely you will not be able to find evidence to support these questions. And there are 2 other questions, and such as, was the reaction more severe when the dose was increased or less severe when the dose was decreased? And another question, did the patient have similar reaction to the same or similar drug in any previous exposure? So those kind of questions, although they have high value, but they just, the answer we found usually not present in the notes. But the beauty about this Naranjo is that despite that you have lots of questions not available, but which is okay, because so that's one of the beauty of Naranjo, because they have the range. And so it's okay, you don't need to answer all the questions, just because, and also, they have do not know. If you do not know answer, you still score. So therefore, even with a number of questions that you could identify, you can still like build up this particular scale. And so, which is very nice with this, methodology. Next one. So the question for us is that, it is very label intensive and for this Naranjo and also need special training. Not everyone can do the Naranjo. So we are very fortunately to collaborate with pharmacovigilance experts and who are expert in Naranjo and was be able to train a whole team and so to annotate. And so it's very painfully long. So I think it would be very difficult for people using it as everyday daily basis and for Naranjo. So we thought that can we automate this process. So therefore we develop approaches to automate this Naranjo question answering. Next one. So for this, just as we did with MED dataset, and so we create a cohort that we can be used for supervised machine learning. So with this cohort, and so we select clinical notes of patients who were administered one of the 6 anticoagulants, and then physician annotators manually examine those notes, and so they are all longitudinal data, and then provide answers for each Naranjo questions. And experts provide 2 levels of annotation, relevant sentences, and answer for each Naranjo questions. Next one. So here's the data set. So we have annotated a total of about is 991 patients, and with over 1,000 discharge summaries. And so we automatically eliminate question 1 and 6 because they are not answerable, as we described earlier on. So the remaining questions, and so we found, just as we see, so we have 5 questions and were most frequently answered by the experts. Next one. So the data sets we have is so on the left is different anticoagulants, and then the number of unique patients and that has been administered those medications, and the number of discharge summary that's available from those patients. And so those are the annotation statistics record that we have over 1,000 and discharge summary has been annotated. And so those are the distribution of unique patients and discharge summaries across different anticoagulants. Next one. So here's examples of Naranjo annotation. So we annotation at 2 levels. So on the paragraph from the EHR, because the space, I just only show 1 paragraph here. And so upon arrival to ER, which is emergency room, and patient developed massive coughing, grunt, and hematemesis. And so this one sentence is relevant for Naranjo questions, and then also the answer, specific Naranjo questions, and for this just based on this sentence information. So the Naranjo question would be: did the adverse event occur after the suspended drug was administered? So the answer is yes. Next one. So the data sets we have with those annotated data, we resulted in over 183 and discharge summaries, and it is doubtful, which means the Naranjo score add up to be 0 or less, and possible, which is the majority category, and we have 900 and over 900 notes and has been judged to be possible, and probable will be like 283, and notes has been. And definitely there's only 3 out of more than 1,000 notes. And so the distribution of answer for selected 5 questions are, question 2, 3, and 5, and 7, and 10. And so they are ranging from, yes, no, do not know. So for question 2, and is more than 1,600 yes, and 139 no, and 666 do not know. So you see, like some of them, so a lot of yes, and sometimes do not know is quite a lot. And so with this data, and then so we are able to develop supervised machine learning to automatically for each questions, and we were able to identify the answers and to evaluate, and we we put this data into training and then testing, and then to get performance. And next. So the model we use is a deep learning model. We use a multitask learning model. So the multitask learning essentially has two tasks. First is the model automatically identify which sentence is relevant. And then the second one will be the loss, which is whether, a Naranjo question answering has extract the right answer for the questions. And so on the right here, you show the model. So here, so basically the main sentence here, for example, in ED and H in hemoglobin of an INR, 3.6 and marine stool, and so this kind of sentence that you show in the boat here, so he was found to have this and then rectal exam and receive this kind of stool. And so that's first judge, so that's not input sentences has been represented and using LSTM and then using attention with attentions and the represented and the sentence represented and representation has been later on input. And so to incorporate representations from the context, such as the sentence that occur before these relevant sentences and the sentence occur after these relevant sentences. And in addition, the entire EHR notes and has been used and to encoded into representations and to be used and eventually concatenated with other representation for the classification task. And so next one. So here's a performance for each questions and for Naranjo questions and with different models. And so we experiment with two kinds of models. One's pipeline model. So what does pipeline model means? So it means we first identify whether a particular sentence is relevant, and afterward we independently judge for each relevant sentence whether it is for each Naranjo question, whether it's answer yes, whether the answer is no, whether the answer is do not know. For joint model is that we just take in, and as a joint learning and basically learn both tasks at the same time, and then output and output performance will be the classification and to answer the Naranjo questions. So we found consistently that our joint machine learning models and joint model outperform the pipeline-based models. And we found, and we also try and some other, to increase the performance because we found in some cases, for example, or we found like the relevant sentence is relatively small because of course you have EHR notes, you have lots of sentences that are not relevant, right? So therefore that you have this kind of like a score and distribution. So where, majority of sentence not relevant, that could potentially hurt performance. So we did something called a downsampling where we like select, less negative sentences as part of training. So we found like in some cases that downsampling actually improved the performance, in other cases they don't. And so so we found for the micro average and so which means that we at each individual level, annotated instance level, so we found a high performance. And so overall it is over 98%. And so for the F1 score, and so the reason to have this high performance is because we have a lot of negative sentences and negative, and so therefore it's not surprising. So and then we use macro average, which is average based on the labels and the choice of the labels. And so we found and the performance, into the lowest one is 0.36 and to the highest one 0.52. And so that's actually reasonable because the data we have is relatively small. And so with this actually you see the model actually can perform and reasonably well, and for even though the data we have is relatively small. So so we believe is that if we get more annotated data, this performance can be before they improved. And so, but at the same time, the annotation is bottleneck. And so it is very label intensive annotations and so on. So, so that's really the bottleneck and for this project. Next. So, so one thing we try a different approaches. We say, well, you know, since annotation is hard and training is hard, but we can have other way to increase the model performance, and which is we explore the calibration. And so the calibration is that, you know, when you make the NLP output, and so how confident are you? You know, so if you predict, you know, particular answers is, you know, is yes, and so how confident you are if you extract medications, and how confident is your model, like, you know, so whether, you know, you extract that's medications, and so what's the confidence, you know, is the confidence 90% or if confidence 10%? So we want to perform calibrations and also to help improve the performance. So that's why, you know, we work on this calibrating structured output predictions for natural language processing. Next. So the calibrations provide confidence scores with NLP and structured output predictions. And so calibration is very important for healthcare, and it's because it's high precision, right? So because if you like, you know, so output, and, you know, if you like, you know, want to see like patient have particular disease, and so you better to be as high performance, high accurate, otherwise it could potential like problems, right? So if the patient does not have that disease, and that's going to be a lot of trauma and so on. So therefore that it is important for healthcare, and especially to judge the output of particular machine learning models. And so the widely used methods are often defined as binary or multi-class problems, and not for structured outputs such as NLP. So we propose a general and calibration schema, and for structured output and in neural network-based NLP models. Next one. So we use the calibration framework from Kulasho, and so was published 2015 to define a general structured calibration schema for NLP system with the following properties. It can use any binary class forecaster to calibrate and predict confidence for a defined output entity of interest, and provides better calibration than standard methods for both in-domain and out-of-domain samples. And the forecast confidence can also be used to rescore output entities and improve underlying predictors and predictor performance in both in-domain and out-domain. Next one. So we define calibration schema for the following NLP tasks in part of speech and name entity recognitions, question answerings. And so here, including our made data sets, and we also want to see the generalizability of the system. We also try other data sets that were public, you know, is well established in the NLP community, including Pension Bank and Calling, and then for another medical data set, we use the EHR QA. And so in general, we found neural network models such as BERT, and which is widely used, and so a state-of-art model, and have calibration errors ranging from 3.5% to 30% on this task. So we therefore evaluate our calibration scheme on each of those tasks. Next one. So here are some experimental details, obviously, that, you know, so if people interested can look at our papers, and because that would post a lots of details, and here just at high level. So we're using some of uncalibrated predictors models, including BERT, distilled BERT, and BERT CLF. And so those for name entity recognition tasks. And so evaluation tasks, we evaluate including part of speech, name entity recognitions, and question answering. So for question answering, we focus on extractive question answering versus not abstractive question answering, because we focus on the structured NLP output prediction. So, and for the forecasting features, and we include model outputs and also uncertainty and entity of interest and specific features and distribution uncertainty using language model perplexity. And so, so the evaluation criteria we use in expected calibration error. Next. So we found the calibration and overall improve almost every task, including the MATE 1.0 and the name entity recognition task, and the classify performance after, so because another beauty about the calibration is that you can rescoring and can further improve the performance. So it also improved the performance, and which result in state of art and for MATE dataset for name entity recognition task. Next. To be 0.84, and so that's improvement over the and before, like 0.82 F1 score. Next. So the conclusion is that the structural prediction models for NLP have an estimate of the expected difference between the model confidence and accuracy as high as 30%, and versus in our cases, we provide a general calibration schema and to calibrate only those output entities that are relevant for model predictions, and it can use any binary class and calibration methods as a plugin to improve the calibration for output entities of interest and enrich the forecast training and improve calibration performance and restore the output entity to improve the predictor performance. So this kind of calibration not only improve the performance, but also it's very important that when you try to deploy a particular machine learning model and change from particular one data set to another data set, as we all know, like hospital, they don't share their data. So therefore that most likely, if you want to make your NLP system, so most likely you will channel one hospital data and then take the model out to predict, to be deployed in another hospital. So this kind of calibration will be very powerful in terms to decide like, how good it is your system when you like try to move the model to another hospital data. Next. So that's was exactly what we try to do, like because so we have over 200,000 patients and which result like millions of EHR notes, and then we have access to a huge data set, which is the VA, where we have more than 10 million patients and 8 million patients, and have billions of EHR notes, and so we say, well, can we actually move the model, we change from the UMass Memorial Hospitals and to deploy into the VA system to get more ADEs. And so, but before we did that, and we want to be very careful. And the reason we want to be careful is that we want to make sure that, so all can be done in the private, and secure fashion. And so because when we look at the literature, nobody has studied and whether the models, and especially for deep learning models, and that trained on EHR data, whether they are secure and whether they are prone for the attack. And so therefore we look into a membership inference suspendability of clinical language models. Next. So the underlying, as we said here, is that so most of the machine learning models, including NLP, and then we work on sensitive data warehouse such as electronic health records, and because it's almost impossible a lot of times to fully de-identify the nodes when you train the NLP model on. So most of the NLPs and machine learning model, they train on large EHR data set, and which include all the identifiable information like in the notes, right? Because it is okay to remove the identifiable information from the structured data, and then there are some notes, and so would probably describe sometimes sensitive information. So there are the identification tool available which we use, but still like even with all the removal, and so but it still has a little bit suspendability in terms of sensitive data and could be used for malicious use. And so the question we try to address is that whether if you train especially for deep learning models, you train on this data, and how safe are they? Can you actually train on those machine learning model with one hospital system? Can you actually just give to other people and that to deploy to the other to another hospital? So that's a question we try to address here. How safe are machine learning models trained on EHRs? Next one. So we look into something called differential privacy. And so differential privacy describes a promise made by a data holder and or curators to a data subject. So the premise is that you will not be affected and adversely or otherwise by allowing your data to be used in any study or analysis, no matter what other study and data sets or information sources are available. So basically, for the membership, so we use something called a membership inference. So giving a model, which is a machine learning model, which you train on the sensitive data, and also a data sample. So for example, if someone, for some reason, they just copy and obtain a particular, EHR note from a particular patient. And so can this person or the attackers infer whether the data sample was a part of the training set? So why is that relevant for the privacy? So it's relevant, for example, we have the MAID data sets, right? And then we publish the MAID data set, and so people with user agreement can obtain this data set. And the data set is fully identified, which is fine. And then we train our machine learning model on these data sets. And then from the publication, people can see that, this data, it is obtained from the Memorial Hospital. And then if someone else and, some person, with bad meaning, and so somehow obtain one node sample. And so the question is that how likely that this person, and based on the model, machine learning model we release, which trained on the EHR data, which is a MAID data set, they would be able to find out that the node sample this bad person keep processed to, and would be able to identify that sample actually belongs to and has been used as part of training for this machine learning model that has been released. So therefore, and we'll be able to infer that the node that he got actually belonged to Memorial Hospital. So I know it's kind of like this is like most strict cases, and for the privacy, because we just want to make sure that everything we do is highly secure, highly private. And so we purposely chose this one membership inference as extremely very difficult cases, right? Because you have lots of assumptions. You say the bad people, and they actually take control of one data. But we just want to make sure that if with such cases, and what are the and the likelihood that the person for the security breach, and so what because nobody has done this, and so we're going to find out, and so what would happen. Next one. So here's what we found. So we used the most state-of-art models and some of the state-of-art, and so BERT, and so that's encoder-based. And this BERT is also encoder-based, and the GPT is decoder. And and we run different epochs. We have lots of more results. And so we released the paper on the archive, but the paper itself is under review and for a particular conference. And so, but you can see the paper at the archive. And so here's what we found. So what does it mean? So basically, if you train your model, and the more epoch you train, so you actually security leak has been increasing. But the slope of the increase of security leak is much less for the encoders, but for the decoder model like GPT is much higher. And but the overall actually, the privacy linkage and for this, membership inference attack, and actually it's relatively small, so it's and it's a point, and point is not, like a 6%, and for here at 4 epochs, but it increased probably and would increase a little bit. And so next one. So here's
Hi, Dr. Hong. Just because we are just 5 minutes away, I think we should just take some questions as well from the participants. And if David, you can read out a couple questions, and we can definitely answer the remaining questions via email.
So, so should we just take questions now? Should I just quickly wrap up?
Yeah, you can just quickly wrap up in a minute or so, and then we can just take a couple questions.
Yeah, so maybe we move these slides to the next one and do the next one. So basic conclusion we have is that the large language model have higher empirical privacy leakage than smaller language models. And we found randomly masked language model have lower privacy leakage than autoregressive language models. And when we train in data using DPSGD is a particular differential privacy and can reduce empirical privacy leakage while ensuring the increase in model utility. So the user, and another thing is that the user with real profile and maybe more vulnerable to higher privacy leakage. So that's a conclusion. And next one. And so for future direction, next one. So I think the bottleneck for every NLP is, since we supervise machine learning, so we need more annotated data. So that's very label intensive, but it is important to build those high quality annotated data. And of course, unsupervised learning and need to be developed and domain adaptations. And we believe that it's important to continue to develop Naranjo question answering, and which include annotations and machine learning models, and also data integration model development based on multi-source data. And finally, and we just saw recent one article 2020 that people has developed semi-supervised tool development that can be like adapt, and actually was developed by Harvard group. And so that can be used for, so for pharmacovigilance, but so it remains to be seen whether the tool can be used. And so that's it. And next one, just thanks the group. And yeah, so my students on the job market for faculty stars 2022. So if you're interested, contact them. And other, next one. So others, our physician collaborators and faculty collaborators and my group in the next one. And we thank the funding agency and for the support. Next. Yes, and the next, and that's my contact information. And the questions.
Thank you so much, Dr. Yu. This is a super interesting presentation. You covered a great deal of material on several areas, and I think all of it's relevant to Sentinel, particularly as EHR data are being incorporated. There were a number of questions in the Q&A. In the interest of time, I think what we'll do is circulate those to you by email. Perhaps one question you could answer though is it possible to share your slides and or any of the code that was used in these studies via, for example, GitHub?
Yes, and so the slides, of course, I already so I think I would think the slides will be public available, right? So I'm happy to share the slides. I already sent the slides to the group. And so for the codes, and so we actually for the Naranjo, I think we released the code, and we put so the data like made 1.0 data is public available. You just need to have signed a data use agreement. So I mean, most of our work here is public available, and so we are a little bit cautious, like before releasing the data for because this
Sure.
for this because of privacy concerns and so on. So therefore that we actually and some of but all the the NLP models described, like you can get the data, you can train the model, and as long as you have the user agreement, and you should be able to get both data and the model.
Great. Well, thank you so much. I want to thank you again for presenting at today's webinar. As a reminder to all participants, this session has been recorded and will be available through the Sentinel webpage. And you can find details about this recorded session as well as future sessions at the Innovation Center and Methods Seminars on the website, sentinelinitiative.org. This concludes our session. We hope to see you all again next time. Thank you and have a great day.